Hello everyone, welcome back. Here is Orillusion. In the last video, we learned how to use WebGPU's adapter and device objects. Today, we continue to learn how to create rendering pipelines. Firstly, we create a function called init pipeline. We pass this device in, and we need to declare this device here. In fact, we rarely use the real TypeScript syntax in the previous code. We just use it to check the API. But in fact, when we pass variables, we need to declare what type of this device parameter here. Otherwise, in the scope of this function, the device will not have any auto-completion hints. Alright, let's take a look at what type of this device is. It is actually a type of GPU device. Because the device is returned by this request API here is the GPU device. We could attach the tab to here, and then we can get helpful code hints when we call here. Okay, let's go back and look at how to initialize a pipeline. In fact, pipeline is some programs that make the GPU run in turn. This is called shader. So for a rendering pipeline, what shaders are needed? What is the order of execution? In order to make it easier for beginners to understand the configuration of the pipeline, we need to understand several principles of computer graphics. The images we see are actually 1 pixel by 1 pixel. By combining them together, they can form the basic point, line, or surface. As for surface, the most basic polygon is triangle. Complex polygons can actually be formed by combining multiple triangles with each other. For complex polygons, if the resolution is large enough, human eyes can't actually distinguish the edge jaggedness. Then the final image will look like a smooth transition curve. Actually, GPU drawing is to draw dots, lines, and triangle surfaces. Almost all graphics APIs we know, including GPU hardware, will do a lot of structural optimization and design for this process. So today, the general rendering pipeline can be roughly divided into 5 steps. So first of all, we need to write the relevant data into the memory of GPU through the CPU by the program. When we need to draw a graph, the GPU will combine the point data and additional buffers we input and input them into the vertex shader for calculation. The vertex shader will eventually output all the vertex coordinates of the graph. For example, if we want to draw a triangle, the vertex shader will finally output the coordinates of these 3 vertices. The GPU will then combine these 3 vertex coordinates to form a triangle. And then the rasterization process will be performed. So simply put, it is matched image with pixels. We will eventually form a fragment of the pixels enclosed by the area formed by these 3 points. Then input the fragment information to the fragment shader. Finally, the fragment shader does individual color processing for each fragment. This step can be very complicated. For example, combined with the relevant vertex information and the external texture information, we can simulate various light and shadow effects and form complex graphics. But the sense of this result is to assign each pixel the color. Then in the end, we can perform some color mixing and finally output a triangle graph that we can see. In this process for developers, the steps that we can operate and control, in fact, only this vertex shader and fragment shader. So creating pipelines is actually creating these 2 shaders. Now let's look into the code. Firstly, we can declare 2 variables. One is called vertex shader, the other is fragment shader. We can create the shader program we want through the Create Shader Module API in the device above. This API is very simple. We just need to attach the code here and then tell the browser the code as a string. The browser will help us to compile this piece of shader language into an executable program that GPU recognizes. Today's goal is to draw a triangle, so we can write this piece of WGSL code directly here as a string. WGSL is a new shading language proposed by W3C for WebGPU. It is not substantially different from the other shader languages, but the syntax is slightly different and is more convenient to compile and be checked in the browser. In this video, we mainly focus on the process of rendering, so we will not introduce the relevant grammatical usage of WGSL. We only need to know the purpose of these shader programs is to output 3 different points information according to the index. Note here, we do not recommend writing code directly here in the form of strings in the function, which is not readable and not easy to be maintained. We can import WGSL as a separate module through import. For example, we can import vertex from triangle.vertex.wgsl in the related directory. Then we can assign this value into the code directly through the variable. The error occurs here because import cannot parse pure strings by default. It must be a JavaScript or TypeScript file with an export object. Otherwise, TypeScript can't parse this import. We can use the grammar feature of with here and add a question mark and a row after it. You can import the file as plain text and copy it directly to the vertex now. The syntax of the question mark plus the row character is not the standard syntax of import, nor the syntax of TypeScript. It can be recognized by us because we introduced the with client definition package in this TypeScript config file. In the first video, we introduced a definition package for WebGPU and also a definition package for with. Then after including this, we can add some with grammatical features to TypeScript. So here we use the feature of loading strings. In the same way, we can import fragment shader, red.frag.wgsl in this directory, and add question mark row to this file. Then we can directly assign this fragment shader to fragment shader variable. This fragment shader is even simpler. It just outputs an RGBA color with 1001, which is just a pure red. This color scheme uses the range from 0 to 1 represent RGBA. It's actually the format called BGRA8 norm, which is we use by default on the web. If you use other formats, then in WGSL, we should also use the representation of the same format to match external colors. After creating 2 shaders, we can create pipelines through the device create render pipeline API. There are 2 versions of this API. The first one is synchronous creation, and the other one is asynchronous creation. We recommend asynchronous form in WebGPU, so we can free JavaScript from suspending and waiting as much as possible, and effectively reduce the load of the CPU. If we create multiple pipelines, the overhead savings will be significant. So here we can directly pass these 2 parameters and set the pipeline vertex and fragment parameters, respectively. You may also like to check doc to learn more about the detailed content required by a descriptor in the definition of TypeScript. Here, in order to save some time, we code directly. In the vertex shader, we need to pass the vertex shader we just created through the module field. It's the same for fragment shader, we need to pass fragment shader in as well. Secondly, we also need to tell the pipeline what the entry function of each shader is. Just like what we did in JavaScript. We call these two functions through the run function, which is the entry function. Then in this WGSL, we can actually define multiple functions. And these two shaders are very simple. It only defines a main function. So we need to assign these entry points to main. The same for fragment. Here the fragment is marked red because we can see that it is missing a field called targets. Targets field is used to indicate what the output color format is. Because fragment shader outputs are actually individual pixels colors. And WebGPU supports many color formats. So we need to tell the WebGPU pipeline here which color format we are using. And this format must match the format that we used in the canvas. Otherwise, it cannot be rendered properly. We can directly pass the default format in the browser we just used in the initialization phase and then into the GPU texture format, and also quoted this format here. And then we can directly use the format field to assign values to targets. Note here, this is a JavaScript shorthand form, which is actually format:format. Finally, we can also code the parameters of primitive, the join method. Here we can directly use the default topology, which is triangle list. And we'll explain the specific meaning of this later. Alright, a basic pipeline is created. And in general, we may create multiple pipelines and buffers, groups, textures, and extra that pipeline needs to use. But because drawing a triangle is very simple, basically all the data is hard-coded in these two shaders. Because we mainly want to demonstrate the entire drawing process. So we don't have to care too much about the creation of other elements for now. We'll introduce how to create GPU-related resources and how to use them dynamically in shader in the following videos. Now we can return the asynchronously created pipeline through await. The arrow here, because we haven't written this function as an asynchronous function. Then after this, we can easily get the pipeline object and then return it. In the same way, we can use await in run function to get the returned pipeline, which is going to be used in the next stage. Okay, now all the preparation work is completed and we can start real drawing work. This is all for today. Thanks for watching and welcome to subscribe our channel. I'll see you in the next video.